Hello, everybody. This is Chapter 5, Selected Example Problems. And let's start. 5.1 is where we'll start. Says, the wrist is made up of 8 small bones called carpals that glide back and forth as you wave your hand from side to side. A thin layer of cartilage covers the surface of the carpals, making them smooth and slippery. In addition, the spaces between the bones contain a special fluid which provides lubrication. A bioengineer measures the contact force between two nearly planar bone surfaces in the joint, as well as the force required to make them move. The contact region between the two carpal bone surfaces is indicated in an X-ray image of a human hand shown in Figure 5.6. The minimum force required to move the joint is 0.135 newtons. And the contact force is 12 newtons. What is the coefficient of static friction in the joint? We have F applied equals F contact mu S. So F applied over F contact equals mu S. So 0.135 newtons divided by 11.2 newtons equals 0.012. And there are no units on that coefficient of static friction. It's a unitless number. Continuing on 5.2. In example 4a, we considered a skier accelerating under the influence of gravity down a slope of constant angle theta. The free body diagram in figure 432 shows two forces, the skier's weight and the normal force. To make the problem more realistic, we should add the force of kinetic friction. If the coefficient of kinetic friction between our skis and the snow is mu k, what is the skier's acceleration? I guess we're going to write it in terms of these values, terms of these symbols. We have force due to gravity, mg sine theta, and minus the friction, mg cos theta mu k equals ma. We don't need these m's. And so I guess that is our answer. Let's see, is that our answer? Oh, they took g out. G times sine theta minus cos theta mu k. Okay, is mu subscript k. All right, equals acceleration. All right. Yeah, this is friction is the normal force times the coefficient of either static or kinetic friction. Static if it's not moving, kinetic if it is moving. All right, 5.3. Up a ramp. The block shown in figure 5.10 is given a push up a ramp of angle 32 and released with an initial speed of 31 meters per second. The coefficient of kinetic friction between the block and the ramp is 0.42. How far up the ramp does the block travel before coming to a stop? I like the way they solved it. It was interesting. Let's see. V naught equals 3.1 meters per second. Theta equals 32 degrees. Mu k equals 0.42. And remember, that is a unitless number. All right, so we're using VF equals V naught plus acceleration times time. And X final equals X initial plus V naught T plus 1/2 AT squared. All right, So V final 0. V naught equals negative AT. So T equals negative V naught over A. All right, X finals we're solving for, this is 0. So we have let's see, I'm just going to be substituting my value for T in that equation. So I have X final equals V naught times negative V naught over A plus 1/2, and that's G sine theta. Oh, they didn't write it as G sine theta. Okay, so the word, all right. We'll keep that A out of there for a minute. One half A times V naught over A squared. All right, so this is working out lovely. This is X final equals V naught negative V naught squared over A plus V naught squared over 2A. So that's going to equal to V naught negative V naught squared over 2A, 1/2 V naught squared. All right. All right, and let's see. I think I'm not done. Let me pause, get some board space. All right, for the acceleration, you're going to have the acceleration on an incline is G sine theta. But now we have A equals, and now we have to deal with the friction, which is going to be G cosine theta times mu k. And this is going to be in the negative direction, right? It's going opposite the direction of the force. Both the acceleration due to gravity and the friction are slowing the block down or whatever. Yeah, the block down. So now our final equation is going to be d, the distance, equals v naught squared over 2. These negatives will cancel. G sine theta plus G cos theta mu k. And I'll let you put those values in and solve for yourself. It's a pretty good problem. All right, in example 5.4, you're pushing a block against the wall and you need it to stay there. So you push a block of plastic that weighs 32 newtons against a wall with a force of 55 newtons. As shown in figure 5.14a, the coefficient of static friction and kinetic friction between the plastic and the wall. I could have sworn I did this, but I can't find my calculations. Anyway, we'll do it again. Are 0.41 and 0.40. Does the block remain motionless? If not, what is its acceleration as it slips down the wall? If it's going to remain motionless, that the friction has got to equal mg. All right, so we have the friction is going to be the push times mu s equals mg. All right, let's see. What do we have here? We've got you push is 32 newtons and mu s is 0.040 equals mg is oh, this is 55 newtons. And mg would be 32 newtons. So let's see what we got there. Let me just use their answer. Let's see. Okay, so it's going to slip because we compare this is less than that. All right. So it will slip now. And the forces, mg minus f equals ma. So mg was what? 32 newtons? No. Yeah, 32 newtons. Minus, was this? $55 newtons times 0.41. Is that it? 0.41? 0.40. Oh, I used the wrong value in the last part, but you could just go back and substitute 41 equals ma equals 32 newtons divided by g times a. All right. All right, so we have, let's see. I don't know what this is, but your book says it's going to be negative 30. This is m, 32 newtons. That's right. Mg is that. So that's m. So we could do, it's going to be negative 3.1. Go ahead and solve that. Meters per second squared. All right. And that was 5.4. All right. Example 5.6 says, let's see, where are we? 5.6. A rock is attached to a string of length of 0.76 meters and swung in a circle at constant speed. The string makes an angle of 68 degrees to the vertical. What is the speed of the rock? The weight of the string is small enough that it can be neglected. All right, so we got some scenario like this. This is 68 degrees, and you got, this is a rock, 0.76 meters here. All right, so some of the forces in the y, T plus mg equals 0. All right, some of the forces in the x, I'm sorry, T cos theta. T cos theta equals mg. And this should be, I boo-booed. T cos theta minus mg equals 0. All right. All right, sum of the forces in the X, T sine theta equals mv squared over r. All right, and like I did in that other problem, I'm going to divide the two equations. So T sine theta divided by T cos theta equals mv squared over r divided by mg. So tan theta, these cancel and the m's go. So tan theta equals v squared over rg. And so if you want to solve for v, v is going to equal to the square root of tan theta rg. And that was 5-6. For 5-7, you really should read the couple pages before it, but it says, a car follows an unbanked curve at a constant speed of 18 meters per second. If the coefficient of static friction between the tires and the road is 0.55, what is the radius of curvature required so the car does not skid? All right, so they took equation 530, which says mu s equals v naught squared over gr and solve for r. So r equals v naught squared over g mu s. And you put the values in, 18 meters per second, quantity squared, r equals. G is 9.8 meters per second squared. And let's see, mu s is 0.55. Put those values in and get 60 meters. R equals 60 meters. All right. Problem 5-8 says, a gourmet pizza chef flattens a ball of dough into a disc that has a radius of 0.15 meters. He then throws the dough in the air, rotating it as he releases it. One region of the doughy disc has a lump, which extends from 0.05 meters to 0.15 meters. Find the ratio of the force experienced by the part of the lump close to the edge to the force experienced by the part of the lump closer to the center. All right. Let's see. Lump equals 0.05 and then to 0.15. So F equals mv squared over r. F1 and F2. F1 equals m. V is 2 pi r, the radius, right? Over t. And this is squared. And there's over r. And F2, this is R1. And that's R1. F2 equals m 2 pi r2 over t. And that's all over R2. So this is, if we take all the constants out, we have just simply F1 over F2 equals R1 over R2, because this is squared too. Yeah, these are going to go. And one of those is going to go. So that's it. And that concludes your example problems from chapter 5. As always, read the chapter, practice the problems,